Hello and welcome to Glue Lecture 6. Today's lecture should kind of walk you through a little bit of this idea of how robots are going to behave using the framework introduced in Module 6 this week in Dr. Egersted's lecture. So hopefully it'll help you with Quiz 6. So this week in lecture, Dr. Egersted introduced this kind of scary-looking hybrid automaton that has lots of complicated guard conditions, and today we're just kind of going to break through those and sort of show you how we might move through this automaton as we try to navigate towards a goal. So we have these behaviors: go to goal, this is actually a controller, you go to goal, follow wall, navigating around the obstacle counterclockwise, avoid obstacle, and follow the wall of the obstacle, navigating in the clockwise direction. So we're going to answer this question of what does this look like on a robot? So in our little setup, we have some robot here. He has a heading given by this black arrow. We have our obstacle in red. Around this obstacle, I've drawn a line in gray that represents this delta distance away from the obstacle at which we need to switch to avoid obstacle when we get inside. And then here, the little orange star is our goal. So now, where does the robot wake up in terms of this high-level description of the control? So this first arrow points right here into you go to goal, which means the go to goal controller will be running right when the robot wakes up. So this is the behavior we start with. So what does this look like in our scenario? We have this vector here drawn in red that points to our goal, and this is the direction along which you go to goal will drive us. And remember that on the robot, kind of at this lower level, we're thinking of these controllers with these equations, right? So our go-to-goal controller is going to cause us to drive our current state, x, to this goal using some gain given in k. Likewise with the avoid obstacle controller. And then with follow wall, we're just rotating the direction that AO, avoid obstacle controller, takes us, and we're rotating that by 90 degrees, depending on whether we're going clockwise or counterclockwise, which way the 90 degrees goes. And remember that that's given by this rotation matrix here. So if you see something like, where you have, say, 0, 1, 1, 0, notice that this could be a rotation matrix. There might be some theta that satisfies what this matrix looks like that means that this matrix is causing a rotation of a vector. Anytime you see kind of a symmetrical structure like this in a matrix, say on Quiz 6, keep that in mind. And remember that our robot is implementing this controller up here, U, in terms of V and W and our actuator wheel commands. And we know how to go between V and W and the wheel commands back in Module 2. That's where we learned that. So while we have this high-level kind of controlling automaton, there are these other things going on kind of at the lower level on the robot. But for now, we'll just think, okay, we know that when you go to goal is running, our robot is going to drive towards that star, directly towards it. So let's watch that as that happens. We're driving towards it, and now, all of a sudden, we're at this point where we're within delta away from our obstacle. So let's go back to our automaton and see if that changes anything. And indeed, two of the guard conditions are that when we're inside of this radius delta, we might have the condition where we need to change. So let's look at the other half of both of those conditions where we're looking at this inner product between these vectors defined by these control laws, the go-to-goal controller and the follow-wall controller, both clockwise and counterclockwise. And this is really going to determine, once we're inside this delta range, do we follow the obstacle clockwise or counterclockwise? And when we're talking about vectors here in the Euclidean space, so we have our follow wall vector and our UA avoid obstacle director. This vector, this is the direction we would drive in if we were operating under this controller or this controller or this controller. So now, how do we kind of decode this condition of this inner product? So with these vectors in the Euclidean space, our inner product is just a dot product, and so we can write it as the magnitudes of both of these vectors, here, for example, with the clockwise follow wall controller, and then the angle between those two guys. So this is really the important term, right? Because this is going to vary between 1 and -1 in the following way. So if the two vectors are collinear, then the angle between them is 0. The cosine of that is 1. So that would satisfy this condition, right? When they're exactly perpendicular to each other, the cosine of that is 0. So we would not satisfy this condition. And then, of course, when they're completely open and the angle between them is pi, we get this -1 value. So we know that our vectors, this cosine term, is going to vary between these values. And if it's 0 or -1, then no matter what these magnitudes are, it's kind of irrelevant. And so really what we're worried about is when we're in between these two cases, between 0 and 1, where this is going to be greater than 0. So you can kind of see now directly from the picture that in this case, my angle between the clockwise and the avoid obstacle is a little bit smaller than between these two, right? Because these are going to add up to 180. This one looks like a little bit less than 90, so that means we're going to follow that clockwise rotation that way. So we can see that these two conditions are satisfied now. And so we move from operating under the go-to-goal controller to now the clockwise follow wall. And at this point, when this is true, we note the time d tau, because that's an important condition for whether we switch later, given by this guy down here. So we note that it's d tau, what time it is, or not what time it is, but how far away we are at the goal here at d tau. So we mark the distance from our goal at d tau. And now we follow wall. So we're going to follow this new kind of pink vector. The robot's going to keep moving forward. And now we've actually gotten a little bit closer to the goal, right? So let's go back to that automaton. Let's look at the condition that might cause us, here we're in this state now, what might cause us to leave is if we get within the distance delta, well that's not going to happen, right, because we're following the wall, or if we get closer to the goal than we were at time d tau, or at time tau, so the distance at time tau. And then again, this other inner product that we need to consider. So let's look at those two vectors now. So here we have follow wall, avoid obstacle, and go to goal. Now we're interested in whether the cosine of the angle between these two vectors, avoid obstacle and go to goal, is between 90 and 0. And of course, in this case, we can see that that's more than 90, so we're going to stay with following wall because we don't satisfy both of the conditions to go back to go to goal. So we continue to follow wall, continue to follow wall, and now we're getting closer to that point where now this angle here is less than 90. Our inner product between these two vectors is now greater than 0, and so we switch. These are our two conditions we needed to satisfy, right? We switch back from follow wall to go to goal. Great. We've made it all the way, and this is kind of where we're home free because we're not going to encounter any more obstacles. But if we did, we kind of go through that whole process again. So you can see how this overall hybrid automaton, switching our controllers, we get to this, what we did, right? This path around the obstacle. And we made the goal. So I hope that this helps you with some of the kind of high-level behavior questions you're going to have on Quiz 6 this week, and check the forums for more help. And good luck.